So I'm talking about a week from today. I was saying that this will be our last Friday Zoom. We'll Zoom again on Monday, but I'm in the last Friday Zoom. A week from today, you'll be on the 21st. You'll be hopefully up at school at lunch, and you'll eat lunch with us because I want to take the big picture. I want to get a picture of everybody, all my classes, everybody together, okay, on the West Lawn. You can wear a mask if you want, but and then I'll feed people. Now I'll feed everyone. I'm going to have to ask a little bit of money just to recover my costs, like $2 or $3 at the most. But you're going to get a chili cheese dog, chips, drink, and dessert for that. So it'll be a pretty good deal. Now what I'm thinking is, okay, so last night we had a flash off, and I think it comes down to you and third hour. Maybe second hour, but first hour had 3 in there, and they were trying their hardest, but they did pretty well, but I don't think they could beat all you guys. Io, Sophia, people were on fire with getting stuff. So I was going to show you. Io was there last night when I was trying to go through. It's because I stupidly did not record it. I didn't have. It doesn't give you all the chat. And so I had to take screenshots of every page of the chat. 40 screenshots, 40 pages. I printed it all off last night, 40 pages. And it's like a confusing mess because you're going, this is where 2 points is my own fault. I fully admit it. So I fell asleep last night. I was working on taxes too, and I finally just gave up. So today I showed them the stack, and I left it at school stupidly. But I'll look at it this week. I'll give it a shot. If I can't decipher and get it, because it's so, if I can't get it figured out, here's what I'm going to do. That's what I was going to do for you guys anyway. But I'm going to, for anybody that showed up last night, that was at the thing, first, second, third, or you guys, I'm gonna give you a free meal. Okay, so that'll be a chili cheese dog, chips, drink, and dessert for free. $3 value. Woo. I mean, it beats eating a donut, but you got to show up to get it. To Friday lunch, you got to eat lunch, right? Everybody's got to eat. That's what I'm thinking. Unless this weekend, when I look it over, I have a clear winner. If you guys blew away everybody, then okay, I'll just give it to you guys. But everybody was trying hard. It's not first hour's fault that only 3 of them were there. That those 3 that were there deserve some credit. So I think maybe in a twist of fate, perhaps the only fair thing to do is to give everyone that participated, all 21 of you, a free meal on Friday. Anyway, I didn't tell the classes that because they were all up in arms, but I'm thinking about this weekend. Okay, so there's our opening announcements. Let's share the screen here. Moment of truth. Will it work? Yes. All right. My whole program just went on the fritz again today. Just crazy things that are happening. All right, so here we are, class 22, almost wrapping this thing up. Angle of repose. We didn't quite get to that. We spent the whole time on friction. On this is a get your notes ready because this is a wide-ranging, crazy discussion. Just get ready. But look at that. Look what's coming up. Look at that. Look, it's the sunrise. It's the rising of the 6. Woo! 6. 6 more, including this one, 6 more Zooms. That's 4 next week, plus today, plus the Monday of finals week. That is the last Zoom. Flash off, we talked about that. Now I'm still offering Sophia. I saw that she, and I looked at hers, it was very good. She sent in her submission for 6.3 key, student key. This is Avery's, who sent it in last night for number 1. And so I doubt one person will win first, number 1, number 2, number 3. It's 4 stamps. So to you, that equates to 12 points for every one that I use. If I use all 3 of yours, you would get, pretty good. You're going to get 36 points. Okay. But anyway, if you just submit something, you're going to get 3 points. So we're trying to see who can make the best key out of this. And then I'll just Frankenstein it together. What else we got? We showed this, I think I maybe showed this yesterday. That's that I died in 99. There is a David Askey, the film director, but that must really be the ultimate insult for him to have my picture on his obituary. But that's not what got me. That's what got me right there. Director, that is me. Director, I used to be the director of the K-12 science education for Parnassus, this group called Parnassus. And I'm going to stop recording for a second. We talked about it in class, so I thought I'd talk about it here, just so you guys stayed up. You understood what we're referring to. This came to you this morning at 8 a.m. was supposed to be emailed out. So you should have this on your student email, not your parents. I'll send one out to your parents too. I've had a couple of people now have signed up for it. That's cool. If you just want to sign up, all you got to do is sign up for a week and then you'll get the whole summer for me. Not for the other guys, but for me, for you guys, I'm offering 75% off. Because you're my students and you're sort of guinea pigs. I'm going to put a lot of effort into it. I mean, we've spent over $1,000 already. So we're just trying to recoup some of our costs. Because I got the money we've spent mostly on paying my computer people. And I owe them a ton of money now. They're my old students, but I still got to pay them, right? So they've been real cool about it, but I keep promising I'll eventually pay you. So that's why all the money that you give me is going to go right to them. All right. And then we're going to start it for real in the fall. I'm going to do physics 101. And that way, this is like physics, third semester sort of. So I don't expect a lot of people to take my course, except you guys. I want you guys to take it. But the other two, guitar and for Dr. Fournette, you could jump in there yourself. The blue test is due tonight. I doubt you turn it into my front porch. You can just turn it in tonight. You can just submit it by midnight tonight, the blue test. And we talked about this yesterday. I sent you your blue. I sent you your test. So you can look at that, look at your original test, and then just go to scan from the notes, scan it in. And that way it looks pretty. And then it's easy to do it. And then, send that in to me. Submit that on. There's a 6A blue. You'll see it in the assignments. Okay, questions and all that before we get into this crazy topic today. You think what I was talking about a minute ago was crazy. This is crazier. Okay, we good? You're not gonna believe me. You're not gonna believe me today. I have one kid, and I respect this kid, and he outright called me a liar. I mean, to my face. You don't understand how deep that hurts. I got into education. I got into this because of finding the truth. I hate liars. I can't stand liars. I know I have some fantastical stories, but I'm 62. When you're 62, you're going to have some crazy stories. Life's crazy. Anyway, I'll talk to him about it. I have proof. I mean, I'll send you. I'll show some proof on Monday if that makes him feel better. Nothing for stargazing today. I thought this. I ran across this an old picture I had, not of me. I don't know who it is, but I thought that was funny. I got that on the internet. That is Newton's universal law of gravitation tattooed to the wrist. I thought, well, that's not a bad idea. You know, you might as well there's like a book I was showing a kid today. I don't have it with me, but it's all the greatest. It's a little thin book. It's fantastic. And it's all the greatest equations. And this is one of them. This is in there, one of the greatest equations of all time. And it just talks about the equation. Isn't that cool? It's done in a way that's not boring. It's really interesting. So I'm not giving that book away. But this is great. I think you should have, this is one of the top 5. You should have all 5 tattooed on your body in different places. Promoting tattooing here. All right. So yesterday we started talking about the chemistry of friction. We're going to continue to talk about today. That is not us. Hold on. This is us from yesterday. First off, you all slept. Who's got a question about this? This would make another LDF right here. So you would get and this came up today in class. LDFs, London dispersion forces, come in clusters. Like it's not like homogeneously spread out between surfaces. It comes in clusters, and we'll explain why that is today. I swear, some kids thought I was smoking something this morning. No, the truth is stranger than fiction about this stuff now. But this is all true. And it's crazy to think this. A guy named Fritz London, and here he is. I will post this. I may have posted it last night, but I'll post it again on today's. I was off a little bit. I said 1938, and he did do stuff in 1938, but he really started his journey in about 1930. And Fritz London of London Dispersion Forces, he really is forgotten, mostly for 3 reasons. It was the 1930s. He was German and he was Jewish. The Nazis basically said that whatever he's doing is Jew science, and they discounted it all. They also happened to discount Einstein. Oh yeah, that's Jew science. Relativity, general theory was well established by them, but the Germans wouldn't believe it because he was a Jew. Is that nuts? Think of the mental illness you have to have. Lisa Meitner, who was the smartest woman at the time living in the world, and maybe right up there with Marie Curie, maybe one of the smartest women ever to live. She was run out of Germany, and she figured out how atomic bombs work. She's the one who understood, and we have a video of her. We show a movie of her. We ran out of time this year, but it's in this thing called Einstein's Big Idea. You ought to look it up. I think you can find the whole thing now on YouTube. And if I remember, I'll put Lisa Meitner in here. But she was working with Otto Hahn and determined how chain reactions work. And from there, she refused to have anything to do with that. She refused to have anything to do with the atomic bomb because she knew, she'd done the calculations. She knew how many gigajoules of energy are released during this chain reaction. Looking at Einstein's E is equal to mc squared. Her nephew, Otto Hahn, not Otto Hahn, Otto Fritsch, a different Fritsch, Otto Fritsch, did come to the United States and join the Manhattan Project. He was a big player in the Manhattan Project and did eventually drop 2 bombs on Japan. Okay, so all that stuff comes out of the idea that all these Germany had this great trove of scientists that, because of their bizarro, misguided fervor and dogma, they ran them out of Germany. Religion, politics, and science, that is a lethal combination. Modern day, like I say, girls are killed by bombs in Afghanistan because they want to learn something. Here is a magnified view. We thought this was from a student teacher of mine 10 years ago. Now he's big time physics down in Dallas. But he put this together. This is the only thing I don't like about it is it has the partial positive charges on top both times. I wish he'd flip that so that you don't think that the top's always partial positive, the bottom's always partial negative. It's just random. That part's random because of Heisenberg uncertainty principle. There's that, and I'll post this. And then there's this. This is more details, and it also talks about what we're going to talk about today. This kinetic, the kinetic situations of a microscopic scale. This is a picometer scale. Today we'll look at a micrometer scale. Who's here? We got 7 of you. The usual, right? Hold on, let me see who's with me here. Okay, it's the family here. Yeah. Okay. It's my usual peeps, as they say. Here's more information on London dispersion forces. I'll put this. I got this off the internet somewhere, Wikipedia, but I'll put this up so you don't think I'm lying to you. No. Man, don't ever say I'm lying to you. That's what I don't do. I mean, I might as well get out of education. If I lie to you, it's by accident because I didn't know or I was ignorant of something. All right, so here is a turntable, and just letting you know that's what that is. Maybe your parents have one or your grandparents, but the reason I show this is that, and there's the stylus, right? You used to spend a lot of money on those styluses. Those things cost, I spent $120 on just my stylus alone. You can take that out and put a new one in. It's the needle. It's that needle right there that makes all the difference. And these are the grooves. This is the LP, right? These are the grooves. So when the scale we're on today is this scale. This is a micrometer scale. If I look at, there's another one with the stylus in the grooves. And believe it or not, that produces music. Isn't that crazy? It produces that crystalline quartz crystal there vibrates sideways, back and forth, up and down. And that then is translated in analog. It's an analog translated into a signal, which then goes through your speakers and you hear sound. Isn't that crazy? You know, we figured that one out, right? Anybody know? Who figured out the phonograph? Open up the chat here. Anybody know who figured out the phonograph?
Thomas Edison.
Thank you. There's the zoom point. Thomas Edison. And then so here's an example of a groove, and that's not a mistake. So the that quartz crystal comes along, hits that thing, goes left, goes right, goes up, goes down. That changes. Those are the frequencies. And so you would get in here, you get skips. We're on 20. See, we're on the micrometer scale, 20 micrometers. So you get skips in there sometimes on those albums. I was showing the kids in class an album, and this was an album I had. I know where all the skips are. I know which song the skip is in. And so if I'm sitting on the couch in my living room with my best girl, I know where that skip's coming. And so you had to time getting up to, get a drink or something, to time it just right to make sure you flip that. Otherwise that skip comes in. That's my generation. Talk to your parents about album skipping. Sometimes it'd skate. Oh, anyway, vinyl. I don't know what. There's a vinyl craze. Are you kidding me? God, I was so glad vinyl was gone. Oh, I'm all for vinyl, man. Vinyl sucked. It was terrible quality, all scratchy and all. I'm a purist. Yeah, right. Then CDs come along, and that's totally. And once again, I'm still keeping it on. This has something to do with friction, I promise you. I'm keeping it on the micrometer scale. Now it becomes pits, right? Long pits, short pits, ones, zeros. Spinning, these CDs spun at around 5,400 RPM, which is amazingly fast. 5,400 revolutions per minute is how fast a CD spins. And then there's CDs, which would give you, with these ones and zeros and a red light. We talked about E is equal to H nu last time. Energy equals Planck's constant times frequency. So the greater the frequency, In other words, red is a low frequency, blue is a high frequency. The greater the frequency, the greater the energy, the greater the information you can gather. So on a CD, you can only get about 700 megabytes worth of information. On a DVD, you have see, they're both red light, but a CD, the wavelength is 780, sorry, these pixelates, 780 nanometers. On a DVD, that red light's about 650 nanometers, much tighter. And now you can get up to 4.7 gigabytes on a DVD. Now, a Blu-ray, now you're looking at blue light, and that wavelength is 405 nanometers, much shorter, which makes it a higher frequency. Remember, frequency is how tight the peak to peak is. And look at that. On a Blu-ray, you can get a lot more information, 25 gigabytes, which, you know, I mean, we're used to terabytes now, but still, Blu-ray, that's a lot of information. Okay, so kind of getting off the subject a little bit, but I'm still talking about micro scale. Here's a micro scale. What is that? Anybody throw out what you think that is? It's not grass. Anybody know? I think that's eyebrow hair, somebody's eyebrow. That, or it's on a fly. I don't remember. It's been many years since I found this image. So I don't know for sure, but it looks kind of like an eyebrow, doesn't it? So those are hairs. I mean, they're colorized. It's not really green hair. That, or it's on a fly. I can't remember. But anyway, the point is it's hair follicles. We all know what that is. And who was the first person to draw this for a zoom point? That's a headlouse. We talked about this. Who was the first person to draw this? Who was the first person to see this? Really, you guys are slow today. That was Robert Hooke. Robert Hooke. Remember, he drew the micrographia. He drew the headlouse. People are all going, "Oh my God!" And it turns out that is exactly like his drawing, and that's the stuff that's hanging onto our hair. So now we're on this is an electron microscope. We're still on the micrometer scale. What is that? Anybody got an idea? What is that?
Is that like a dog paw? I don't know.
That, believe it or not, is a spider. Those are spider eyes. Those are the eyes of a spider. Crazy. Microscale. Finally, last one. What is that? Oh, we got one more. What is that?
Are those like window blinds?
Looks like it. That is a double-edged razor, like a shaver. These are hair follicles. So it's shaving your face. So the point is, we think of a razor as really smooth, but look at all the imperfections in a razor. This is like a very new, it's not a really old razor. As I recall, it's a fairly new razor with after shaving somebody's beard. Finally, that's the last one. And the question is, what is that? Anybody got an idea? It's a micro scale. This is all around you right now. It's all in your room.
Dust.
That is dust. Thank you. There's the stamp. That is dust. And this came from a book that I gave away last week. And this woman, she studies dust her whole life. She has a PhD in dust. She wrote a book about it. But in this dust, a fascinating book. In this dust, any kind of dust, there's like dinosaur scales. I'm not sure if that's a dinosaur scale. Kind of looks like it might be. There's spores in there. All these things are hidden in dust. So there's a whole other world in the dust on your floor. There's remnants of people in that dust, not just your fingernails, but somebody that lived in 1840 their stuff is still there in your house. Ooh. Okay. Now, what's all that have to do with what we're doing? With what we're doing? Here we go. Let's go to this right here and this one. Okay. So when I take two objects, two anything, rubbing on something else. Okay, this on this. When I break it to the micro scale, like I showed you, it's more like if you think it's a smooth surface on a smooth surface. Say you sand down two pieces of wood and put them and rub one on top of the other. It's really this. It's the surfaces are really like peaks and valleys. Okay. Now, why do we care? Because the area, this is called the gap. And this is probably want to write this down. These are the gaps. Remember we said, make sure you have a gap between the top surface and the bottom surface. So here's your gaps. The bigger the gap, the less London dispersion forces. And the reason is this. Let's learn here's a new formula for you. Okay. New formula. I don't know how far we'll get today, but here's a new formula. This is called Coulombs Law. First thing you learn in electromagnetism, and it's the force of E and M, electromagnetism, is this dielectric constant, Q1 times Q2 over R squared. This is a constant. It's dependent on the medium between the surfaces, between whatever the charges are. This is charge. These are charges. You going, what's that do with electricity? What's that do with friction? Well, friction's electrical in nature. These are the charges. And this, whoa, not R2, R squared. This is the distance between them. Okay. So, like for instance, if I have a proton and a proton, we know that those are going to repel each other. And you've seen the little iron filings, I guess, like day one of E&M is what we do. And that is Coulombs Law, which dictates how much they're repelling each other. You take a proton and an electron, and they're going to, attract. How much do they attract? Coulombs Law. Well, notice about Coulombs Law that it looks a lot like a law we learned last week or earlier this week. Doesn't that look like Newton's universal law of gravitation? So it's right. The universal law of gravitation is, to remind you, like the tattoo I showed you at the first, force due to gravity is big G, that's that constant, M1, M2 over D squared. That looks a lot like Coulomb's law. These are called inverse square laws. There's a lot of these inverse square laws in physics. An inverse square law comes from, I don't know how to do this with you guys. Let's try it. It's not dark enough in here, but it comes from this idea of intensity. What the? Oh, what? God, what is going? Well, I was going to try and show you this light. See, if I put a light up, you probably wouldn't work anyway. But as I pull that light away, like a flashlight, the further away it gets, the intensity drops off as the square of the distance. It's called inverse square law. The point is that pretty quickly, I have a graph. Pretty quickly, we graph this. We used to graph this in AP chemistry. I made them graph it right here. Pretty quickly, the force between two masses, the gravitational attraction drops off as a square of the distance. The electromagnetic force drops off as a square of the distance between them. So it gets weak really fast, is my point. Oh, one other thing I wanted to talk about that. On this Coulombs law and the combo, that they're both kind of the same. Doesn't that make you start to think that maybe gravity's got something to do with electromagnetism? Maybe. This came up in class, so I'll throw it out there. How much time do I got? 10 minutes. Okay. Here's the sun. Here's the earth. Earth going around the sun. Okay, let's do a gedonks, a thought experiment. Now let's say the sun goes away. Now I'm going to snap my fingers, and it doesn't go red giant. It doesn't explode. It just disappears. Okay, say right now the sun disappears. Are we still going to have light outside? Sun's gone.
Maybe not the sun's light, but light from devices. Yeah.
Maybe some starlight, maybe. Oh, light from like our own electricity generators and stuff.
Yeah.
Oil, whatever. We'll have our own light, but I'm talking about light like daytime. Would it be instantaneous night if the sun goes away?
No,
Why not? Sun went away.
it takes a little bit of time. The speed of light's like 8 minutes from the sun, right?
Okay, so there's a point there. So the sun's light, they're waves, of course. Light is a wave. It takes it 8.3 minutes to get to us. So we'll still have light for 8.3. The sun could have been gone. It could have been gone 4 or 5 minutes ago. We still don't know it yet. What about the Earth's rotation? What will the Earth do if the sun were to go away?
Would our gravity be weird?
The Earth, we'd still be sitting on Earth. That's not going to affect us. The Earth's gravity is not going to change. What about the direction of the Earth, though, if the sun goes away?
We just go in a straight line because
You think Newton's first law, right? Tangential, right? But that's wrong. If the sun went away, we would continue to orbit nothing. We would orbit nothingness. My professor told me that in college, and I said, okay, this guy's full of it.
But how would that work since we don't have any gravitational pull?
Yeah. The thing is, the Earth would continue to orbit nothingness for 8.3 minutes. We would continue to orbit, and there's nothing there, and we're still orbiting it. And the point is that gravity travels at the speed of light. That's another thing, gravity. And then I agree. At that point, Anthony, I agree. Then the Earth would go off tangential. Not exactly, because we're stuck. We would then, I think Jupiter would kind of start to take over. We would still be somewhat stuck in their gravity well, and we'd probably start to orbit Jupiter, some combo Jupiter-Saturn thing. But for about 8.3 minutes, we would orbit nothing. So that makes you think, well, look at that. The force due to gravity is an inverse square law. The force due to electromagnetics is an inverse square law. So maybe there is some electromagnetic aspects to gravity, but gravity is so weak. So I think that I'll tell you what, it's not that gravity and gravity is like electricity, but they're both tied into space-time. We got to admit that. Light bends, gravity is the result of mass bending space-time. Light bends around space-time. So in that, they have commonality, gravity and light. And perhaps that could be the reason for this similarity in equations. Okay. That's all kind of a side note. The main thing I want you to know, here's a new equation for you. It's one of the top 10, certainly, equations in physics, the Coulombs Law. You'll do it when you take electromagnetism in physics. You'll learn this day 1 or day 2. But what's it have to do with friction? Askey, get to the point. Okay. As we come along here, okay, I'll go a different route. I got 6 minutes. Let me go a different route. Let's suppose that I go to Nepal. I travel to Nepal, and now they're shutting down again. Great. I'll tell my story. Let's say I'm going to Nepal, And I go over there and I pick up the Himalayas. Okay. Now, this is just water in here. I'm not drinking. I pick up the Himalayas. I grab the Himalayas, the Mount Everest, K2. I pick them up and then I flip them over. Then I flip them over and I walk across the Pacific Ocean. Now I take those Himalayas flipped over and then I go to Colorado and Wyoming and all. And I set those Himalayas, I flipped over Himalayas. Here they are. We'll draw a little picture here. Here's my Himalayas flipped over. Okay, K2, Mount Everest, et cetera, et cetera. And then I take those, and then here is Colorado, the Rockies. And I then take those Himalayas, I kind of shake them around so that they kind of nestle down into the Rockies so that it looks something like this. Not perfect, it's not perfectly aligned, but something like along those lines, okay? So these are the Rockies and then the Himalayas, okay? And this is the, this is like two surfaces on top of each other from a micro scale. And this is a static situation. I'm afraid to get near that part of the screen. See, it's just discriminatory against left-handers. This is a static situation, and this is called peak to trough. That's the actual name. I just didn't make it up. Peak to trough. Meaning that the peaks of the Himalayas are nestled down into the trough of the Rockies. Now, if this were two surfaces, then remember we said Coulombs Law depends on the distance between those surfaces. I would start to get along here, I would start to get London dispersion forces forming. Boom. See how tight that is? Form. One forms. One forms there. Maybe that's too big, but one forms there. One forms there. And so this is why London dispersion forces come in clusters. So these are all LDFs. This is a static situation. So they've had time to nestle down. Now let's do another scenario where I now take the Himalayas, peaks and troughs, okay? And then I take those and I run those. I go down to Mexico. I pick up the Himalayas, flip them over, go to Mexico. And then what I want to do is I want to take those Himalayas and I'm going to push them over the Rockies and end up in Canada. All right. Well, whenever I'm doing that, it's not going to have time to nestle down. Those peaks of the Himalayas aren't going to have time to nestle into the valleys of the Rockies. And it's gonna shear peak off, peak to peak, basically. Peak. All that's going to have time is the peak to peak. And this is if this guy's moving. It's a dynamic situation. This is sliding. And this is called peak to peak. I'm not making this stuff up. In peak to peak cases, there's a tremendous amount of spot in here where there is just no way, because of the inverse square law, that you're going to get London dispersion forces. And so you'll have some London dispersion forces, but you'll get them at the peak to peak. Boom, a little cluster there, some here, couple here. But all in all, if I draw my picture very well, you're going to get a lot more here on a static situation than you do here. This is actually on an AP exam in that situation. And here's where it came in on an AP exam. I got 1 minute. Let me show you this much, then we'll pick it up on Monday. But here's where it comes in right there. This graph, it's the last thing we'll do. This graph, this is FS equals mu sub s times n. That's one equation for friction. This area is FK. Hold on, I got this done here. Let me show you a better picture, or because we're low on time. Let me show you the end result. the Martha Stewart version. Ah, I'm getting there. Hold it. Here it is. Here it is. There. This is so this blue region is the static region. This is force versus force, friction force versus applied force. So you'll see this in every physics book. That's the static region where two surfaces aren't moving over each other. That's called peak to trough. And then the kind of tan version here, that's where the top surface is sliding over the bottom surface, and that's called peak to peak. Notice this is kind of rough because this is high chaos. High chaos in that part of it. Okay. I went over again. I'm sorry. Well, no, it's 2:00. Okay, so no homework except the Blue Day stuff. We'll pick this up. Don't worry about this sheet. We'll pick it up on Monday. And then we'll wrap up friction on Monday and get on to something else. Okay, you guys are free to go. If you have a question, stick around.
Mr. Askey,
Yeah.
could I use you as a reference for Norman High event?
Well, of course.
All right. Thank you.
Okay. See you.
Yeah. See you. Have a good weekend.
Okay, you too.